Good morning. I welcome you all to the very first lecture, that is the introductory lecture to the course Laws of Thermodynamics. Thermodynamics is the branch of science that describes the basic laws and principles governing the processes of transfer and transformation of energy. The laws are formulated from the observations in nature, while the basic principles as the corollaries of the laws are established through logical deductions following the laws. The science of thermodynamics provides also the relationships between the thermodynamic properties of a system or substance. This helps us in determining the changes in property of a system executing a process. The classical thermodynamics today, you can just think in this manner, as a tabletop rests on four legs, which are the four laws of thermodynamics. They are namely the Giro's law of thermodynamics, which provides the concept of temperature. Another one is the first law of thermodynamics, which puts a quantitative constraint on the conservation of energy, or simply it is the law of conservation of energy. The third one is the second law of thermodynamics, which imposes a directional constraint on a physical process, whether it occurs spontaneously or it is man-made. The third law awares us or makes us aware of unattainability of a state by any system executing any process. Thus, the four basic laws makes the foundation pillar of the classical thermodynamics. Now, as a whole, if we look, we see that what actually we gain from the science of thermodynamics. In fact, the science of thermodynamics provides us the information regarding the feasibility of a process under a given condition, the direction of a process, in which direction a process should occur. Just for an example, I tell you that a chemical reaction, let us consider a chemical reaction, takes place from reactants to products. At some conditions, whether the reaction will take place at all or it will be in equilibrium, the mixture of reactants and products will be given or will be known from thermodynamics. Or at given condition, whether the reaction, net reaction will be from reactants to products or from products to reactants, that means in which direction the reaction will take place, or it will take place simultaneously in both directions, with the net effect in one direction will be told by thermodynamics. Another example, you can see all these things will be discussed afterwards, that a process cannot be made in both the directions or cannot be made to occur in both the directions. For example, let us consider this: a flywheel is rotating with certain RPM, it has a kinetic energy. If you stop the wheel by applying a brake, it comes to rest, and we will observe that the temperature of the wheel and the brake shoe, if you apply the mechanical brake, has increased. That means from the conservation of energy, that kinetic energy is converted into intermolecular energy, which raises its temperature. Okay? But there is no means by which we can utilize this kinetic energy or convert this we can utilize this intermolecular energy or convert the intermolecular energy into kinetic energy to set the flywheel in motion. It is not possible. That means this process of converting the kinetic energy into intermolecular energy of a substance or system is unidirectional. But there are a number of processes which can take place in both the directions, but we have to pay something for it. All these things will be discussed afterwards while discussing the second law of thermodynamics. So, this way the thermodynamics tells us the direction of the process, feasibility of a process, and these are extremely important. This is because when we intend to execute a process or a process occurs in nature, our main aim is to get some useful desired output. for example, useful work, then our objective will be to make the process as efficient as possible, so that we can get the maximum desired output out of a given energy with minimum energy dissipation. This is in the perspective of both energy conservation and energy dissipation, and this is extremely important to design a process, any physical process. And this analysis or this analysis of the processes occurring in any engineering device or engineering plant is extremely important, prime importance, and of primary requirement from the viewpoint of the design of the plant, engineering plant or device. This is known as thermodynamic design, under which condition the plant or the device will work at its maximum efficiency with minimum dissipation of energy and maximum conversion of energy from one form to other. So, this way we see thermodynamics is a very important subject and plays the role of foundation pillar to all branches of engineering, science and technology. And this motivates us to read thermodynamics well. This is a subject of conceptual subject, less mathematics involved with less mathematics, but we have to understand the concept very clearly so that we can solve problems on thermodynamics applied to real cases. Okay. Now, with this introduction, short introduction for regarding the importance of thermodynamics and our motivation to read thermodynamics, why we will read thermodynamics with so much vigor, that I have told. Now, we will start the course with definitions of certain basic terminologies which you have probably known by this time or you have read already, but this will be a recapitulation in that case. That is system. What is the definition of a system? In the analysis of any problem, whether in thermodynamics or in fluid mechanics and heat transfer, any engineering science or in physical science, we always deal with system, the analysis based on a system. So, therefore, we must first start with the definition of system. Let us see that a system is basically defined as a quantity of matter or substance, a definite quantity of matter and substance bounded by some boundaries, contained within some boundaries at the instant of our investigation or analysis. So, therefore, we can write this way, that system by its basic definition has two characteristic features. One is the definite quantity of mass or definite quantity of matter or substance, and it will have boundaries or boundary, whatever you call, and this is known as system boundary. This is the boundary of the system. It will have a boundary of the system. It will have definite quantity of mass. It will have definite quantity of matter or substance. The definite quantity means mass. Mass, the word I am not using at the present moment. Definite quantity of matter or substance, you can call also mass. And it should be defined with a boundary which will distinguish itself, the system, from external things, which is known as surroundings. So, whenever the definition of system comes, this is known as surroundings, which is external to the system, but not the vast external. This is used as external, that external to the system with which the system interacts. That means in its close vicinity, the surroundings in its close vicinity, that is known as surrounding. In fact, when two systems interact with each other and with nothing else, then one system is the surrounding of the other. That means the definition of surrounding and system is not that very clear. That means a system can also be called as a surrounding to other system with which it interacts. So, this way we define system and surrounding. Now, this system is of usually three types. One is known as control mass system or closed system or simply system. Sometimes we use for simplicity system. These three are synonymous term for one class of system: control mass system, closed system or simply system. Another one is the control volume system, or sometimes we call simply control volume. The system we do not use. So, all these terminologies are known and used at different places, or open systems. These are all synonymous terms of a class of system, open system. So, control volume system or control volume, usually in thermodynamics people use this terminology open system, while in the analysis of fluid mechanics control volume system or control volume. Another one is isolated system. Now, a control and mass system or closed system is defined in this manner, that this is, if I just now close this, rub this, okay, we can draw here. A control closed mass system or closed system or only system is defined in this manner, that there is a definite quantity of mass or definite quantity of matter or substances which interacts with surrounding in terms of energy only, but there is no interaction of mass across this system boundary. First I tell this, there is no interaction of mass across this system boundary for this control mass or closed system, but there may be interaction of energy. Here I like to tell you another one thing, that while defining these system boundaries, one thing should be remembered, this boundary may be real or imaginary. Usually we have real boundaries in practical systems. Sometimes for the analysis we can have a real imaginary boundary, but it should obey all the restrictions or definition imposed for the system. For a closed system, the boundary should be such which should not allow any mass interactions between the system and the surrounding. This is the system. While the system can interact with its surrounding in terms of energy, and you will know afterwards or that this energy interaction is in the two form. One is heat and another is work. Both in the form of heat and work the system can interact. So, therefore, what happens is that in this system the mass remains fixed with the fixed identity. That is very important. That means no mass is allowed to go out or allowed to come in. So, therefore, the mass remains same and with the same identity. So, this is the very important feature of a closed system or control mass system, but it can interact with the surrounding in terms of energy and heat. These arrows in two directions means the energy can go from the system, energy can come to the system from the surrounding, either in the form of heat or in the form of work. While in a control volume system, while in a control volume system or simply the control volume, the system boundary allows, here the mass transfer is not allowed cross, but here there will be both mass transfer in any direction. That means mass can come in, can go out, and also energy transfer in both direction in the form of heat and work. So, therefore, control volume boundary allows the mass transfer from the system to the surrounding or from the surrounding to the system. That means across the boundary. All these mass transfer and energy transfer takes place at the boundary, across the boundary of the system. And it also allows at the same time the energy interactions between the system and the surrounding in terms of heat and work. So, this is the control volume system or simply the control volume or open system. So, one difference is that here the mass may not remain same, because the inflow and outflow of mass, if both takes place and they are not in balance, the quantity of mass will not same. So therefore, the quantity of mass may vary. But under some special conditions, if the inflow and outflow of mass is balanced, that means the rate of inflow into the control volume or open system equals to the rate of outflow, then the mass remains same. So it one way resembles the characteristics of the closed system or the open control mass system, that the mass remains same. But still there is a difference. Here, though the mass remains same, their identity changes because of the mass transfer across the system boundary. But here the identity remains the same. That way, a control volume under that special condition where the net mass efflux or net mass influx is 0 keeps the mass inside the control volume same, but not with the same identity. Here the mass remains same with the same identity, since the mass transfer across the system boundary is 0. There is no mass transfer. Neither it goes out nor it comes in. Isolated system is a system. This is a system which does not allow any mass transfer in any directions. That means no mass can come in, no mass can go out. And also there is no energy transfer also. Energy transfer can take place, earlier I told, in the form of work and heat between a system and the surrounding, that energy in transit which can transfer between a system and the surrounding, between two systems or interacting systems only in the form of heat and work, which you will know afterwards. So this energy interactions and mass interactions both are not permissible by the system boundary. That means system remains isolated. He cannot interact with its surroundings or with any other systems close to it. That means the system remains isolated. In that case, what happens? The mass of the system remains same with its identity. So that way it is same as the control mass system or the closed system, and at the same time all other properties remains unchanged. All other properties remain unchanged because the system doesn't interact in terms of energy also with the surroundings. So therefore both these things are crossed. So this is known as isolated system. So these three systems are very important. Now I will give you example of the two systems, control mass, and this is I write as now short CMS, the control mass system. This is control volume system. The example of the control mass system, the most popular example or which we come across in practice is a gas in a piston cylinder. Let us have a piston like this, a definite quantity of gas, a gas in a piston. This is a closed system or control mass system. An example. Here these are the system boundaries, the face of the piston, this wall of the cylinder. There may be both heat and work transfer. Both heat and work transfer. For example, the piston may go up, come down. That means boundary, there is no restriction. Boundary may be flexible, boundary may expand, boundary may contract, but the mass within this system will remain same with the same identity. This will not allow any mass transfer. When piston goes out because of high pressure in the gas, the system delivers work to the surrounding. When the piston is pushed by the external cause, then the gas will be compressed and the work, this boundary will go inside the cylinder, and the work will be done into the system. The similar way the heat may come out and go in depending upon the temperature difference between the gas in the cylinder and the surrounding, and another thing whether these boundaries, that means wall of the cylinder, allows it to do so. So this way there is no restriction of work and heat transfer, but mass remains the same with the same identity because there is no mass transfer. Now open system or control volume system, one example I give you, that is of an air compressor. Let us draw an air compressor. Probably from your popular knowledge you know these things, that an air compressor, so air is taken in and it flows through the compressor and comes out at high pressure. This is air whose job is to compress air from a low pressure to a high pressure, and automatically its temperature is also increased. This is the flow out. And to do so, the air compressor, we are not going into what is there inside the compressor. The compressor, the work has to be put into the compressor. This is put in the form of the shaft work. A shaft is allowed to rotate at some speed, high speed, or the desired speed, so that the work is made input to the air compressor, and this way the compressor works. So this gives an example of an open system, that if we define a system with this boundary enveloping this compressor and this entry and exit line or the pipe, this is a example of a control volume system or control volume. Simply control volume or control volume system, CVS, whatever you call. Why? Because across this boundary there is a mass inflow. This is air coming in. Across this boundary there is a mass outflow, that is air going out, flow. In all practical situations at steady state, the inflow and outflow remains the same. But however, this system boundary permits the mass transfer across the system boundary, that control volume boundary, which is known as control surface. This control volume boundary is known as control surface. So across this control surface there is a flow in, that flow out. That means it allows the mass to enter into the system and go out of the system. And at the same time, in this case, this example of air compressor, the work comes in. And if the air compressor is made insulated, which is usually done, there is no heat transfer between the system and the surrounding. So therefore, work input is there to the compressor. Another example you can have for this system is a pipeline. There is a continuous flow into the pipe and going out, a section of the pipeline, some short section of the pipeline. The flow is out. Here also you can make a control volume like this, inscribing this pipe surface. These are the control surface. Here this boundary, you see that imaginary boundary. I told you there may not be any rigid or there may not be any real boundary. So we consider in this cross section, this plane, as an imaginary plane, that one part of the boundary of the control volume, another part of the boundary. So as a whole, this as a control volume or control volume system. What happens here? That means it allows the mass to come in and to go out. Whether there will be energy transfer, that depends upon the situation. In this case there will be no work transfer, but there may be heat transfer if the fluid flowing through the pipe is hot or at higher temperature than the surroundings, then heat will come out, or in the other way, that means if this is at lower temperature than the surrounding, the heat will come in. So that way it can have heat transfer. There is no restriction of this transfer. Here for example, the energy transfer is there, but the characteristic feature is that continuous flow of mass through the system. Some part of the boundary mass comes in, some part of the boundary mass goes out. So, but not necessarily always there will be inflow and outflow both, but there may be only outflow. That means if there is a tank and you just drain the fluid from the tank, so there is only outflow. Or you charge a tank, there is only inflow, there is no outflow. So either inflow or outflow or both have to be there. That means there will be mass transfer across the system boundary for a control volume system. So therefore it should be clear that the system should be divided into three categories. One is control mass system, closed system, which is usually used or which is generally used in thermodynamics, or simply system. Another one is control volume system, or simply we can tell control volume, or open system. This terminology is used in thermodynamics, while in fluid mechanics we use this terminology control volume. It is control volume system. And another one is isolated system. We rarely come across the isolated system which does not interact with the surrounding. Its boundary is such that it does not allow to interact, that it remains at the same state forever. Okay. Now, after this, I will tell you the two very important terminologies associated with the definition of the system. Two important terminologies associated with the definitions of a system. One is property, these two are very closely related. Sometimes we confuse that when we define property we use the word state, and when we define state we use the word property. One is a typical chicken egg problem type of thing, which one will come first. But I think we should start first the property without the state. What is the definition of the property? Property of a system can be defined as its characteristic features which describe or define the system, rather I will tell which describe the system and specify the system. There should be some, for example, if you tell that this is a system, that means you have to tell the system contains of what type of substance, what is its mass, this contains this amount of quantity at some characteristic features like its pressure, temperature, volume. It is at some, we tell that some amount of gas, that so much kg of gas is there in a piston cylinder at this temperature and pressure. That means we require certain characteristic features to describe or specify a system. This is obvious today and this is nothing great, but I tell how basic, from the basic these definitions came. So we know what are properties. So properties are the characteristic features describing or specifying a system. The properties, like I give you example, pressure, temperature, volume, mass itself is a property. Just for example, there will be a number of properties like that. You will see that infinite number of properties will be defined, that we will discuss afterwards. But you should know at this moment that the property must have certain characteristic features. It should be not necessarily all together sensible. It should be not. It may be sensible, may be observable, measurable, directly or indirectly. Now the property may be sensible, not that it should have all the characteristics together. It may be sensible, may not be. For example, a body temperature is a property which we can sense by its hotness or coldness, that if you touch the system or touch the body itself as a system, then we feel hot, some sensation is there, or we feel cold. That means some properties are sensible, some properties are observable. For example, a body is moving with some velocity, it has the kinetic energy, which is a property, that the energy which is contained within this system by virtue of which it can move with the velocity v, that is this kinetic energy. We can see the movement of the particles. If we have some solid particles moving within the liquid, or liquid itself is moving, if we charge a liquid, you can observe the motion of the liquid, which is also a property, the kinetic energy contained within the system. That will be explained further in details while discussing the first law. So therefore, it may be sensible, may be observable, but not necessarily. There are properties which can neither. Pressure can be sensible. You can put your hand in gas pressure, you will feel the pressure. But there will be number of properties which may not be which may not be observed. They may not be sensible. For example, entropy, enthalpy, that you will see afterwards that properties cannot be always sensible and observable, but properties should be measurable, so that we can know the property from its measurement, and that measurement may be direct or indirect. Some property cannot be measured directly, but can be determined indirectly from the measurements of properties which can be directly measured. Afterwards you will know, for example, entropy. Entropy cannot be directly measured, but it can be determined from the measurement of other properties from experiment. So this has to be measured. This is the basic characteristic features of sensible, observable and measurable directly or indirectly, the properties. Now we come to the definition of state. The state is described by the fixed values of the properties. That means if we call a system is at a given state, that means all its properties, let x1, x2, x3, x4, like that number of properties are there. Number of properties. All properties will be fixed to determine the state. If we tell the system is at a state, means at a state with these fixed values of properties. So fixed values of properties of a system determines its state. The system will be at a given state when we tell, that means it is specified by fixed values of properties. But here two very important concepts come into picture. What is that? That when you define a state of a system with given or definite quantity of matter or substance with fixed values of properties, that means, for example, the property x1, that means it should be same throughout the system. Here another thing you must know from the property definition, that property is of two types. Before coming to the state, property is of two types. One is extensive property, another is intensive property. One is extensive property, another is intensive property. Extensive properties are those properties, extensive properties are those properties which depend on the mass of the system. For example, here I write total energy of this system, total entropy, total enthalpy, all these things will be discussed afterward. You may not know at this time. These are the defined as a whole of this system, and this depends on the mass. So extensive properties, those properties which depends on the mass, whereas intensive properties are those properties which do not depend upon the mass, which does not vary with the mass. But this at the same time, this can be defined at a point. For example, pressure and temperature, these are intensive properties. And this can be defined at a point. Pressure can be defined at a point, temperature can be defined at a point, and they do not depend on mass. For example, two gases at same pressure or same temperature are there in a container divided by a partition. If you remove the partition, the temperature and pressure, the gas will mix, will remain the same. Does not depend upon the mass. Whereas if the energy contained in one part of the container is E1, another part is E2, if you remove the partition, the total energy will be E1 plus it. It will be additive type of thing. It depends upon the mass. If the masses are different, that will be proportional to the mass. The total energy plus the total energy of the another part will be added together and give the total energy. So therefore, extensive property depends upon mass, whereas intensive property doesn't depend upon mass. But the specific values of these extensive properties, for example, specific energy, that means all divided by the mass, that means specific energy E by m, or specific entropy small s is entropy by m, or the specific enthalpy is big enthalpy, that is the H, big H, the total enthalpy by m. The specific values are all now intensive properties, which can be defined at a point and do not depend upon mass. For example, the volume is an extensive property, but specific volume per unit mass is an intensive property. So therefore, this makes the difference between extensive and intensive property. Now here, when we say that property, when you say the state of a system will be defined by fixed values of its property, fixed values means which is invariant with time, and at the same time this should be same for the whole system. Otherwise, what way we will specify? For example, if we tell that pressure P, one of the properties is pressure, we tell the system at some pressure. That means this should be, pressure should be uniform throughout the system. That the system can be specified or expressed by the single value of the property. That means the property should be uniform throughout the system if this is an intensive property. Like pressure and temperature, that means for a system at a given state, we specify by a single fixed value of pressure and temperature. That means there should not be any gradient of pressure and temperature. This state is the state of thermodynamic equilibrium of this system, which will be again discussed afterward, where the system internally there will be no variation in the intensive properties like pressure and temperature. There will be uniform, so that the system can be described by single value of these intensive properties along with the extensive properties, and at the same time they do not vary with time. That is the very essential requirement, and that comes when the system is in equilibrium with the surrounding. And this can come under two occasions. The system boundary is such that they do not allow the system to interact further with the surrounding, makes the system as isolated system. In that case, system properties will not change with time, and if any variation is there for the intensive properties within the system, that will even out, that will be evened out and make it uniform to a single fixed value. Another option is there, the boundary allows all type of energy interaction or mass interaction, but the system properties have become same as those of the surrounding. That means in the with the interacting systems or the local surroundings. Then that case, whatever may be the system boundary, system properties will remain invariant. It cannot interact with the surrounding. There is no difference between the properties which will give the driving force to interact, and that state is known as dead state. Dead state. So therefore, at the very beginning, we should have some primary concept like this, which I have told about the properties of the system and its state, how the state is defined. And to define the state, the system should be in thermodynamic equilibrium, so that system can be expressed by single value of the properties, mainly the intensive properties along with the extensive properties, and that should not vary with time. That way we can define the state of a system. Okay, thank you.